Okay. Morning, Tay. I have that same trouble.
I bet you do.
Anyway. Okay, Tay, I forgot to get it started, so here is number 15 in case you had a question on it. You can go ahead and freeze frame that and check it out. 17. Okay, 17. The deal with this one, and you know what? I'm going to go ahead and just, I'm just going to talk about it. I probably won't walk through the whole problem. Okay. The deal with 17, we'll put this microphone to use here. I've got a new microphone that clips on here. Yeah, actually, it's on the way. I had a chance to get one that I carried around with me, but then I feel too much like a game show host of some sort. Hey, what'd you get for number 17? I don't know. Anyway, so 17 in this case, the negative 2 from the right, it impacts whether this is positive or negative.
Okay.
Because if this ends up positive or negative, the absolute value that's positive is going to leave it alone, and then we'll just move forward with x plus 2 over x plus 2. But if we were going from if this was ended up negative, then that would end up being negative the quantity x plus 2, so those would cancel down to a negative 1. So what we got to think about right here is I'm approaching negative 2 from the right, this is going to be positive because I'm going to get, like, say, negative 1.9, and that's going to give me 0.1 positive. We're going to leave it alone, and then we can work with from there. But the thing is, you just got to think about, is what's inside the absolute value going to be positive? Well, then leave it alone. If what's inside the absolute value is going to be negative, then we have to change it to negative the quantity x plus 2.
What if it's 0?
What if it's 0? On this case, since we're dealing with a one-sided limit, your question's moved. But if it was going 2 from the 2 without left or right designation, we might have a discontinuity, and then it would be maybe no limit.
Okay.
But we would have to back up and see what's happening from both sides regardless.
Okay.
Couple of good questions. Couple really high-level, thought-provoking questions. Good. Anything else? Going once. Going twice. Let's move on. Okay. Today, a lot of our information. Now, how did I lose my pen? Well, we'll go to our backup pen. Seriously, I don't know how I lost it. No, I'm losing it. Literally. Okay. Today we're going to stick in section 2.4. We're going to be dealing with this limit here. The limit as theta approaches 0 of sine theta over theta is 1. We're going to be using that quite a bit. Okay? And there's going to be a lot of algebraic manipulation that is going to be, I think, new to you and maybe a little bit uncomfortable. So we're just going to do example festamania. Okay? We're just going to do problems from the book, and these are things you can refer back to. Because our goal is going to be to massage our expression until it looks like this, and then we're going to take advantage of the fact that we know that part is 1. Okay? So here we go. We're going to limit as t approaches 0 of sine of kt over t. So then we've got this k thrown in. So that makes it so it's not like sine of theta over theta. We have to know what to do with this k. And I really, really, really wanted to make sure not to screw things up. So I've got the solutions manual here as well, just to make sure I'm going down the right path. Okay? Wouldn't it be nice if this was a k instead? If it was, then we're dealing with the same thing. Okay? But it's not. There's not a k in the bottom. So we got to think about, if I wanted to put a k in the bottom, I'd have to multiply top and bottom by k. So that's what we're going to do. I multiply the bottom by k, and we're going to multiply the top by k. And k is a constant. K is like 3, 5, pi, whatever the heck we wanted to make it. It's not a variable. Even though we're using it as a variable, we're using it to represent any constant that's out there, not one specific constant. Okay? Well, we hopefully know that the limit of this, well, I'm actually going to do something technical right here, which is probably wise. I'm now going to change this to the limit as theta approaches 0 of k times sine of theta over theta. How can we do that? Well, kt, the sine of kt over kt is in the form of sine of theta over theta. Okay? So now we're just going to look at how it is and how it's behaving in terms of theta. This k right here, what could I do with that? Well, I could actually take it out. It's just a constant. It's like 3. If I find the limit of this by plugging something in or using a theorem, then I'm just going to multiply it by 4 when I'm done, or k when I'm done. So this is the same thing as k, limit as theta approaches 0 of sine theta over theta. Again, why can we pull that out? Because it's a constant. Because we know that we can go ahead and plug something in, and that'll give us the limit, or we can actually find the limit of that one part and then take it times whatever the scalar might be. Okay. Well, what's the limit as theta approaches 0 sine theta over theta? 1. So k times 1. So my limit is k. So what we're doing is we're going, we don't really know much about this one, but we know sine of theta over theta, so we've got to chase after that sine of theta over theta form. And then go from there. I think we probably need another one. Yes. And I kind of figured that would be the case, because this is different stuff. There's no doubt about it. It's new stuff. But we're going to wrap it up with something that's a little bit more concrete. Okay? So limit as h approaches 0 from the left. We got this leftness thing going on. H over sine of 3h. There's two things different about that. There's a 3 in there where there wasn't a 3 before in my theorem. Okay? And also, if the sign's on the bottom instead of on the top. So I'm going to do a couple different things. Let's do what we just did. We'll worry about this approaches 0 from the left later. Let's go ahead and multiply top and bottom by 3. That's the skill we just learned. Okay? So then I'm going to go, theta. Okay, sorry. I'm writing with pen so you guys can read it better, and then I can't erase. Gosh dang it. Limit. Now I'm going to go theta over sine of theta. Where will my 3 remain? Well, this right here all together makes my sine of, that's my theta over sine theta. Okay? So the 3 that wasn't involved in that transformation still just stays on the bottom. Okay? So I'm trying to do some visual stuff that shows, okay, that all groups together to give me that one magic expression I'm working on. So basically I've got a 1/3. So then that's going to turn into 1/3 the limit as theta as theta approaches 0 from the left of theta over sine theta. Well, you know what? That's still not exactly what we're looking for, is it? Because usually we have sine theta over theta. Well, now we're just going to do a little trick. Is that true? Can I take that, flip it, and put it on the bottom? I can. Okay? Because it was kind of like saying, if I had something to the -1 power on the bottom, I would flip it and bring it up top. So these two things are equivalent. So now we've got this this new thing that it's, okay, I've got this on the bottom, and technically, even though I don't know if I would write this next step, I would say I've got the limit of s theta approaches 0 from the left of 1 over the limit as theta approaches 0 from the left of sine theta over theta. Again, you probably wouldn't have to write that because we've got these theorems before that say I can take the limit of the top and the limit of the bottom, and that gives me the limit of the whole thing. So anyway, here's what we got. 1/3. What's the top? What's the limit as theta approaches 0 from the right of 1? 1. Because 1 is always 1. Okay? As theta approaches 0 from the left of sine of theta over theta? 1. Does it matter they're talking about from the left? Not at all.
Can you speak a bit now?
I'm sorry. Okay? Doesn't matter at all. Why? Because our theorem says that as the limit as theta approaches 0 without regard to side is 1. So that means that from the left it's 1, from the right it's 1, it's just 1. So I get 1/3. So let's kind of do a little summary here of kind of how to approach something like this. Still get into this magic form. And then from there, I think, you can kind of sprint right to this if you want, just so your eyes can see, oh, okay, now I've got sine of theta over theta. That's 1 over 1. 1 over 1 times 1/3 just gives me 1/3. At any point in time, if there's a step you don't get, hey, let me know. Stop me. All right, Lee. You having some trouble? Oh, okay.
All right.
Okay, you're. Oh, okay. Okay. I just didn't want you to be distracted. I was going to help you. Okay. Okay, here we go. You guys are going to like this. I don't know if that's sarcasm or not. It depends upon where your skills are at. Tangent. Okay. In terms of tangent, what is that in terms of in terms of our other trig functions, what is tangent? Sine over cosine. It's sine over cosine. Okay. So we're going to have to go back to our trigonometric identities and definitions and stuff. Let's go ahead and just review those real quick, okay? Let's find a little blank spot. Tangent is sine theta over cosine theta. I didn't review these first. I probably should have. Okay? Another way we can write tangent is 1 over cotangent. Okay? And likewise, cotangent is what over what? Cosine theta over sine theta. Okay? And just the reciprocal functions in general. I've got cosecant of theta is 1 over sine. Okay? Secant theta is 1 over cosine. And I think that's basically all we need to review, really. So if those aren't on the tip of your brain, I understand. That's why we went back over them. Write those down because we're going to use those a little bit here and there. Okay? Okay. So we've got a couple things going on. I don't know if I like that too. Yes, we've got to convert to sine and cosine eventually, but we've got to get this to where that 2 is gone, or we turn this into a 2. First of all, I can't magically put a 2 inside a trig function. Okay? So you'll notice that, like, say, up here, okay, the only place we could magically put a k was outside of the trig function. If it was already there, we can go ahead and multiply top and bottom by k and bring in the k. That's okay. But in this case, we got that 2 that I don't like because there's not a 2 inside my tangent. So what should we do? Well, we're going to modify this. We're going to multiply top and bottom by the same thing. That it'll get rid of that 2. Just 1/2. So I'm going to multiply top by 1/2. Going to multiply bottom times 1/2. Okay? Is that legal? Yes. As long as I multiply top and bottom by the same thing, we're okay. We're doing fine. So then let's go ahead and simplify this. Limit as t approaches 0 of, now we just have t on the top, and now I've got 1/2 tangent of t, not theta, on the bottom. So now I've got something that at least looks like I'm going to be able to do some work with it. Okay? How about we get that 1/2 outside so we don't have to carry it along the whole time and it's going to confuse the issue? So I did 2 things. I pulled the 1/2 on the bottom out front, but to do that I had to flip it. And then I just rewrote tangent as sine over cosine. Okay. Comfortable? I shouldn't say comfortable, but are you with me? Because if I were you, I'd be a little uncomfortable right now. Let's do some new stuff. Okay? So now how are we going to rewrite this? Well, we still don't have the right form, and that cosine's giving me grief. Cosine's not going to give us too much grief because cosine of t as t approaches 0 is 1. And I'll cross that bridge when we get there. I'll give you some evidence of that. So this is just simply going to be 1. That's not crazy end of the world stuff. Okay? Let's do some hocus pocus. Okay, now what did I do? In my head, let me just make a note over to the side. I looked at this like this. And then I flipped and multiplied. So this is, by flipping and multiplying this, I get the cosine up top. And by bringing that down bottom, I get the same thing that we kind of did the last problem. If I flip it, I got to bring it to the bottom. So now we've got everything we can go ahead and find the limit of. I have a 2. Limit. What's the value of this bottom part as we approach 0? 1 times 1. And cosine of t as t approaches 0 is 1. So we just get a value of 2. Let me convince you that the limit of cosine t is 1. Well, think about your graph of cosine. Look at your behavior around 0. It's approaching 1. That's it. Okay? Let's do one more. And then, I don't know, maybe 2. We'll have to see. Okay? Because we need to, right now I sense we're in still a high state of disequilibrium. I want to get that better. Okay, so here's what I did. I multiplied top bottom by 1/2 to get this t over some trig function of t. Pulled that out and then rewrote all this so there is a specific sine of t over t. I probably should check these and make sure I'm right, which we are. Okay, here we go. Let's do another one. This one I think you'll like better. Limit as x approaches 0 of 6x squared times cotangent x cosecant of 2x. Obviously, we're going to do a bunch of trig simplification. Obviously. Okay? So, limit as x approaches 0, 6x squared cosine of x over sine x times cosecant is 1 over sine. So then I've got 1 over sine of 2x. So consider what our goals are. I want, if I had a 2x there, that would be great. If this wasn't here, it was elsewhere, and I had an x up there, that would be great. Right? Because that's that stuff we can work with. So now what we got to do is massage this, steal x's from someplace, move the cosine around, and now we're going to go ahead and get it into a form that is more of the form sine of 2x over x, stuff like that. Okay? Limit as x approaches 0. So if I had, I'm going to take this cosine and just move it over because that's kind of shows what I need to do. If I had an x sine x and a 2x sine of 2x, where could I steal the x and 2x from?
6x.
Yeah, the 6x squared. Okay? So if I would take this and this, the x and the 2x, and have something out here, so this all gives me 6x squared so I can maintain some level of consistency from one step to another. What do I need here? I need 3. Why? Because, take a look at it, 3 times x times 2x gives me the 6x squared that I had before. So I robbed everything from that. And I'm going to skip a step here. This right here When I flip that, the limit of this is going to be 1 over 1, right? When I flip this, the limit's going to be 1 over 1. Okay? And then I just have the limit of 3 cosine x. What did we say the limit of cosine was before at 0? 1. Limit's 3. Okay. I think we better let that percolate for a day with some practice. Okay? This next one is going to make so much more sense to you. We're saving the best for last. Okay. Okay. Okay, so I get the limit as x approaches infinity of 2x to the third plus 7 over x to the third minus x squared plus x plus 7. There's a very simple, straightforward rule on how to deal with these. Okay, first of all, you need to notice that now we don't have a number to plug in. We're looking at infinity instead of 0. Okay, so that's an important designation. Whenever I have something where it's a polynomial and I want to look at what's happening when it gets infinitely large, here's what I do, is I find the largest power of x, and this will make sense to why we're doing it after you see it. We're going to find the largest power of x and divide every single term by that power of x. Okay? You'll see why here in just a little bit. So here's what we're going to do. Limit as x approaches infinity of 2x to the third over x to the third plus 7 over x to the third over x to the third over x to the third minus x squared over x to the third plus x over x to the third plus 7 over x to the third. Okay? What allows us to do that? Well, we're multiplying the top by 1 over x to the third. We're multiplying the bottom over 1 over x to the third. Totally legal. Okay? I just picture Tay watching this from home going, ah! Okay. It's just the support of people around you in these situations is helpful. So now I'm going to simplify this, because you see there's a ton of stuff we can simplify. X approaches infinity of 2 plus 7 over x to the third over 1 minus 1 over x plus 1 over x squared plus 7 over x to the third. Okay. Why did we do this? Because now we can picture what's going to happen as x gets larger and larger and larger. This first term, 2, is always going to stay 2. What's going to happen to 7 over x to the third when I plug in huge numbers? That's going to get closer to what? No, not 1. What? 0. Because I've got 7 over infinity. 7 over infinity cubed. That's 0. Okay? 1 is going to stay 1. 1 over x. What's that going to get closer to? No. Now, when x is getting huge? 0. We got to consider what our target is when x is getting arbitrarily large. 1 over x squared? 0. 7 over x to the third? 0. So I get the limit of that is simply what's left over, 2 over 1, which is 2. And we are going to, trust me, we're going to do one ugly day of this, and then we're going to do a summary as to what patterns we're seeing, and then we're going to be able to avoid all this and just get right to the answer. Okay? So, But does that make sense, though? I'm just seeking out the largest power of x, dividing everything by that power of x, and seeing that if the top's not keeping up with the bottom's getting huge, then it's getting closer and closer and closer to 0. And then we're just left with the 2 and the 1, which we'll see a pattern in that tomorrow. Okay. So here's what I wanted to do. Where am I at? Okay. So today, page 108, numbers 21 through 27, odd. (51 through 55, odd). And I never took attendance. Okay, so when you start working on stuff like 21, look back at the examples. Try and get 1 or 2 of those done before you leave so you can lean on those around you. Try and get into that sine of theta over theta